Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! Today's show is about thunder and lightning. The physics aren't breaking, but it's fundamental. It puts mental back in fundamental, if you will. So the deal with thunder and lightning is that, as a child, I'd heard many descriptions for how and why they worked. Some people said thunder was just the sound that clouds made as they rubbed together. Other people said that lightning never struck the same place twice. Angels bowling, angry hammer gods, thunderbirds. People say all sorts of things. So, back when I was working on my master's degree, I was thinking of starting some kind of physics outreach. Anyway, the first topic I decided to look into was thunder and lightning because, hey, nobody has a good understanding of it anyway. And what I read blew my mind. Thunder and lightning are pretty well understood. They are simple and they are fascinating. So, I've honestly been waiting 8 years to do this show. Anyway, in preparation for my intro, I decided to look onto Yahoo Answers, otherwise known as the best place on the internet to find out how uninformed everybody is on a subject. And it looks like everybody already knows where thunder and lightning comes from. At least everyone on Yahoo Answers knows. But I don't care. I've been waiting for this show for 8 years, and now you'll just have to endure it and act all smug and nod smilingly at your earphones when you hear me explain things that you already know. You'll have to endure it because you love me, and sometimes you humor the people you love to make them happy. So that's it. Thunder and lightning. So the thing about lightning is that it lights up everything around you, but you only get a glimpse. That's why I like lightning. And that's why I like short stories too. Today, I've invited on Elizabeth Bear, the speculative fiction author. In 2005, she was the winner of the John W. Campbell Award for Best New Writer, and since then she's won 2 Hugo Awards for her stories. She writes novels and short stories, and she first drew my attention with the Hugo Award-winning novelette Shoggoths in Bloom, where she accurately captures the nature of people in Down East Maine. I also like the stories Boojum and Mongoose, which she wrote with her collaborator, Sarah Monette. So some of these stories have been recorded on podcasts, and on the webpage I'll link to all the different podcast episodes that feature her stories so that you can have a listen too. Also, the SF Squeecast just won the 2012 Hugo Award for Best Fancast. Hello, Elizabeth Bear, and welcome to the show, and congratulations.
Thank you. I'm absolutely thrilled to be here. And I feel like I can bring you some good news because Sarah and I just published a third story in the Boojum Mongoose continuity exclusively as a podcast. It's up on the Drabblecast site.
Amazing!
I brought you a present!
I love those giant flying space fish monsters so much. So, Bear, for you today, I've assembled 2 of my finest titanium physicists. Arise, Dr. Amanda Bauer! Dr. Amanda did her PhD in Austin, Texas, and she's currently a super science fellow at the Australian Astronomical Observatory in Sydney. She studies galaxy formation, and she also blogs under the name Astropixie. We'll also link to your website on our website, Amanda. So, Elizabeth, I tried to find a real fulminologist for you for the show. That's somebody who studies lightning. But I didn't know any. So instead, I've got a really exciting guy, and people call him the Lightning Kid. Arise, Zach Weinersmith! So you might know Zach from his multiple award-winning webcomic series, Saturday Morning Breakfast Cereal, or from his fantastic podcast, The Weekly Weinersmith. You might even know him from episode 9, where Jocelyn and Dave and I try to explain warp drives to him. But he's got half a physics degree, and I'm happy to have him in my corner today. Alright, let's talk about lightning. So the story of lightning starts with cumulonimbus clouds, and there's something crazy going on inside cumulonimbus clouds. All of this gropal, all of the water particles, all of the snow inside of it, all the ice crystals, end up bouncing against each other as they pass each other really violently. And this causes the particles to get electrically charged.
You can think of lightning as a form of static electricity. In the same way that you shuffle your feet across carpet, or occasionally you touch your car door and you get sparked. The cause of that is as you're shuffling your feet, you're picking up extra electrons. And so you're getting a negative charge, even though you don't know it, until that doorknob or that kind of feels that negative charge and it produces its own positive charge. And then when you get nearby, you have a spark. So lightning is essentially that spark. And the reason that it can happen is because inside of the cloud, you've got all these water droplets forming, kind of natural process of evaporation and condensation. And these particles are shuffling against each other and they're freeing electrons, or they're building up a negative charge because of that. So it's just a sort of natural process. You build up this electric charge, you get a separation so that the negative charge sinks down to the bottom of the cloud, and then the ground, or the planet, feels that, forms its own little positive charge, and the spark between them is what we see as lightning.
So you want to imagine a cloud, and in essence there are different parts of the cloud. Some of the cloud has gone up from high in the atmosphere down to mid-level. Some of the cloud is moving upwards. Some of the cloud has been sitting there for a while. So it's full of all of these different constituents. There's parts of the cloud where there's lots of this gropal. There's parts of this cloud where there's lots of ice crystals. In essence, these bits have rubbed against each other because sometimes, the gropal's going down, the ice crystals are being swept up in an updraft, and they rub against each other, and then the gropal ends up with a negative charge. It steals an electron from the ice crystal. It's kind of like rubbing your head on a balloon. And your hair steals electrons from the balloons. The balloon ends up with a static charge. Your hair ends up with a static charge, right?
Right.
So if you imagined a cross-sectional diagram of one of these cumulonimbus clouds, what you would see is there would be large concentrations of charge based around, the parts that had stolen the electrons and the parts that hadn't. Near the top, there'd be a whole huge concentration of positive electrical charge. So something had stolen electrons from that region. Then near the bottom, there would be a whole bunch of areas that are just full of negative electric charge.
You've polarized your cloud.
You have polarized your cloud. The thing is that it's not bipolar quite. When physicists go in to study these clouds, there are often multiple poles. So there's multiple regions where there's negative charge and multiple regions where there's positive charge. And the reason for that is, in essence, different regions have different stuff in them, and different stuff steals or gives away electrons depending on what it's hit and what temperature it's hit. But in essence, you end up with a bunch of clusters of charge. Over here, there's a big cluster of negative charge. Over here, there's a cluster of ice crystals with positive charge.
Okay, and you can get cloud-to-cloud lightning because of that?
You can get cloud-to-cloud lightning because of that. 75% of lightning that happens is cloud-to-cloud lightning. Essentially, it's just the electrons on one side of the cloud want to be over where there's a positive charge on the other side of the cloud, and then make a lightning happen between them, and then travel along that lightning. Up until now, I've been kind of waving my hands and talking about positive charges and negative charges in a cloud. But 1 in 4 times, lightning comes from the cloud, hits the ground. Where are the positive charges in the ground? In essence, what happens is, you have this big negative charge. You have all of these electrons in a big cloud sitting right above the Earth. It's 2 kilometers away, but that's pretty close. Electrons repel each other, right? They push each other apart. In essence, this big cloud of electrons pushes all of the electrons on the ground beneath it away. So you end up with a local region right under the cloud, right under this concentration of negative charge that's positively charged.
All right.
And in essence, when you get lightning that goes from the cloud to the ground, what's happening is this negative electric charge is saying, well, the ground in general isn't positively charged. In general, the ground is neutrally charged, but there's a patch right under me that has a positive charge. These negative electrons are going to try to get to that positive induced patch that's right under the thundercloud. So essentially what happens is all of this electrical charge, it sets up a bunch of electric fields that are really, really strong. Now, they're not quite strong enough to break down air. So air is an insulator. It's a thermal insulator, but it's also an electrical insulator. And what that means is that if you take a battery, imagine one of those 5-volt batteries, it's got two terminals right next to each other, right? There's the knobby one and the sucky one. And somehow, even though those terminals are right next to each other, there's less than a centimeter distance between the two, the battery's not discharging. There isn't current passing between the two.
Not unless you stick it against your tongue.
Not unless you stick it against your tongue or keys in your pocket. Right, so air is an insulator, and what this means is usually air doesn't let charge move through it. So these positive regions and these negative regions are stuck. The electrons are stuck over in the negative regions even though they want to go to the positive regions. So the electric fields in the system have kind of a trick that let them tunnel through the air. In essence, they're building a tunnel between the negative charge and the positive charge. Air is neutrally charged. It's like, so imagine that it's all made of neutral hydrogen, because that's nice and easy to talk about. You got a positive charge in the nucleus and then an electron. The positive charge in the nucleus, when it faces this big cloud of electrons, the positive charge is going to be attracted to the negative charges. The electron, on the other hand, is going to be repelled by this big cloud of electrons. It will want to move away from it. And so what you end up doing is kind of pulling the electron and the proton apart. The positive nucleus will want to go one way towards the cloud. The electron will want to go to the other way, away from the cloud. The amount of electric field required to do that is called the breakdown voltage of the gas. So air has a breakdown voltage. It's 2 to 3 million volts per meter. Okay, so if you take a meter span of air and you put a 2 to 3 million volts across it, then the air molecules between these two big plates will get pulled apart and will become free electrons and free nuclei. So in essence, there are these big clouds of charged particles inside these thunderclouds, and they want to get to the ground. But the problem is, there isn't enough electric field to rip the electrons off the atoms to make a good conductor. So there's a trick to doing this. It's kind of a devil's in the details thing, and the answer is lightning. Alright, so let's talk about lightning. You can describe lightning happening in 2 steps. The first step is, if you were to draw lightning on a page, you would get this kind of jig-jaggy shape, right?
Mm-hmm.
So the first step in lightning formation is the formation of that jaggedy shape. It's called the stepped leader. So it comes down out of the cloud, and it forms one segment, one line at a time, and it takes about 20 milliseconds to reach the ground, and each segment is about 50 meters long. And so one forms, and then the next one along branches off of it, and then another one forms after that, and it forms line by line like you're building things out of sticks that you're sticking together end to end, right?
Mm-hmm.
So one will form, and then there's a 50 microsecond pause, and then another will form, and then there's a 50 microsecond pause, and then another form. And you can see this on really, really fast photography. And in essence, you see the lightning growing down from the cloud. Jag, 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 jag. Sometimes it splits into different branches. Each time another segment is added, the whole stepped leader flashes.
So that's why if you see like ultra high speed photography of a lightning bolt, before the actual bolt, you see the sort of dimly lit fingers coming down from the clouds. And then you get one big bridging spark and the other ones sort of fade out.
So when this stepped leader touches the ground,
as I understand it, there's a thing that happens where leaders, both descending from the cloud and descending from the ground, and where they touch is where you get an actual ground strike. Is that?
Exactly.
That's a correct interpretation. Okay.
So you've got this electric field that's occurring in the cloud, how this negative charge coming down. The ground kind of feels this negative charge, and so everything like the top of your head or the top of a tree or the ground pushes up these little positively charged leaders as a result of that. But it's those negative things and positive things that are reaching for each other. There's a lot of different potential connections that they can make, and they're all searching for each other. But as soon as one actually connects, that's when you get this shuffling of charge and a big lightning bolt.
Once it gets to within 50 meters of the ground, another branch will start at the ground and move up and connect. And once these two are connected, once there's a continuous path from the charge concentration in the cloud down to the ground, you get something called the return stroke. And the return stroke is the time when all of the charges, all of these electrons inside the cloud, rush down this tube and into the ground. And that's the flash you see as lightning. In fact, it tends to happen more than once. It will flash once, and then this charge concentration up high in the cloud will send off a little filament, a little lightning tube to another nearby charge concentration, and that will drain out. And then it'll send a tube to another one, and then that will drain out. And so you get several of these pockets draining, one after another, 3 or more times usually. Those are called the return strokes. And so that's essentially what you see when you see lightning flickering. You can vaguely perceive because it takes 50 milliseconds between each return stroke. But in essence, that's what you're seeing when you see lightning.
Because it's already got this nice, fully ionized pathway that it may as well use.
Yeah, that's right.
Making a whole new one.
That's right. Once they have the escape route, the other nearby ones follow that escape route. So it turns out the physics of this stepped leader and the way it works is completely understandable. So I mentioned before that this ball of charge up in the cloud doesn't emit a high enough electric field to cause the breakdown voltage of the air. But it turns out that the little tube of lightning, the charged leader itself, does. Okay? So nobody knows how the charged leader starts. Nobody knows where the first little tube of ionized gas comes from outside the cloud. There are probably lots of theories on it. But what happens is, once that little tube is formed, once there's one little tube, there are regions of that tube that can cause enough concentrated electric field for the breakdown voltage to occur. So I want you to imagine you've got like a 2x4, and you've drilled holes in the 2x4, and you've stuck light bulbs, clear light bulbs, down in this. So they're not glazed, they're just regular shiny light bulbs that you can see through. And you turn them on so all the lights are shining. So imagine that you're holding this 2x4, maybe a foot long, and you're looking at it from different angles. What orientation will the light be brightest on that 2x4?
So you have a bunch of light bulbs all in a line.
Yeah.
Which way will it cast the most light? Is that the question?
Yeah.
If you face it directly toward the observer.
Beautiful! Oh, Bear. That was wonderful.
What's behind door number 2?
No, that's absolutely right. You got it right. And the reason is essentially because if you look at it straight down, you'll see every light bulb in a row. So it's super extra bright. So imagine that you have your stepped leader. Essentially, you have a big tube. You start out with a tube, and it's right full of electrons. Now, these electrons will be pulling nearby protons towards them and pulling nearby electrons away from them. Turns out that even though all of the electrons generally in this system don't have enough oomph to rip the electrons from their protons, if you look at the system from the very edge, if you stare straight down the tube, and together, if they're all aligned like that, there's enough force from there to rip the electrons from the protons. So it turns out that the very tip of that tube is where the breakdown voltage will occur. So it turns out that what's going to happen is you have this big tube of electrons. There are so many electrons packed into that tube that at the very tip of the tube, it's going to ionize another trail. It's going to make a new tube of ionized gas that comes off of the very tip of it. Do you see what I'm getting at?
I think so, yeah.
Yeah, so how can that happen? It turns out that there's lots and lots of electrons in there. They're pushing all the electrons nearby that are stuck to protons away from them. They're pulling all the protons towards them. All you need is one electron. You just knock one of the electrons of that gas out, and it will rocket away from your tube of electrons because it's being pushed so hard. All you need to do is split them apart a little bit, and that electron will start to accelerate. And as it accelerates, it bumps into other atoms of gas. And as it bumps into these other atoms of gas, it knocks their electrons off.
This sounds very much like the famous mousetrap and ping pong ball demonstration of nuclear fission. Apparently, this was early on, and I think it was in the Manhattan Project. They filled up a gymnasium full of mousetraps with ping pong balls on them to demonstrate this to a bunch of visiting politicians, and had some guy toss one ping pong ball into the middle of the gymnasium.
Right.
And you can imagine what happened next.
That's brilliant. Oh, that's amazing. Can you imagine being like the grad student who has to set those up, and then you misplace
sore
one?
fingers for the rest of eternity.
Jeez. Thankless. That's amazing. Yes. You knock one of these electrons off, and it just cascades a whole bunch of electrons along its path off. And so as a result, you end up with a line of new ionized gas. And that new line of ionized gas is the next step in the stepped leader.
Ah, okay.
And so what happens is, as soon as that gas is ionized, all of the electrons in the previous line, and all of the electrons in the cloud, they're all packed together. They're unhappy. They say, hey, we can move down into that new space. And so they all rush down the tube into the new segment of ionized gas. And that's this flash you see as it builds up. Because when electrons move through gas, they bump into things, and that produces light. So in essence, that's why the whole stepped leader flashes as these lines get made on the way down.
And that's the same process that produces a fat blue spark when you touch your cat, only in macrocosm.
So in essence, what happens is you have the step leader, step, all of the way down, it's just full up. The same, say, electron density as up in the cloud. All of the electrons that possibly can file into each of the tubes as this forked pathway gets forged down towards the ground. As you mentioned before, sometimes what can happen is near the ground, because this thing, as it gets closer and closer to the ground, it will induce a positive charge on the ground. It will chase away the electrons in the ground and make the ground more and more positively charged. Sometimes what you can get on the ground is, it's called a positive streamer. You can get one of these little arcs of ionized gas moving up from the ground, which will then try to reconnect with the tube. And in essence, that's exactly the same process, but instead of negative charge, it's positive charge. Instead of electrons being pushed away, it's electrons sucked towards it. But essentially you get these two arcs, and then if they touch, then there is an uninhibited pathway, as I said before, from the cloud into the ground, and then all of the electrons move at once. So now we're talking about something called the return stroke. And this is when the lightning flashes. This is when you see it. This is when it gets really big. What happens is, this stepped leader, it's packed full of electrons. It's full to the brim of electrons. You let some of them out at the bottom. The ones at the bottom will start moving first. The ones at the bottom start moving out, down into the ground. The ones above it get the message. They start moving down. The ones higher up, they start moving down. And so if you watch a lightning, oh God.
A stroke of light.
If you watch one of these strokes of lightning, you'll see it, the luminescent part will start from the ground and then move up to the cloud. And in essence, that's what's happening. It's like a traffic jam. All of these electrons are saying, oh, hey, I can move. And as they start to move, they bump into things, and that's what causes it to be bright.
So Zach was saying earlier something about an experiment relating to this?
Yeah, so you see that in essence what you need to get the electrons to come from the cloud to the Earth is one of these pathways of ionized gas. So in theory, you could just ionize the gas yourself. And so apparently this was actually done with some limited success where they thought, well, if we just shoot a laser at the cloud, it'll heat up. I believe the idea was just to heat up the air enough that it would ionize the gas. And so the idea is you just artificially create the tube Ben was describing, and then what should happen then is the lightning should come right at you.
There's no way that could possibly go wrong.
Yeah, no, it's bad science. Nothing ever goes wrong. Presumably you have a Frankenstein set aside to absorb the lightning, and then wreak havoc. But I assume you could probably just set up a lightning rod that would gather the lightning. So, but what's cool is I think theoretically you could justify by saying, well, there are situations where lightning might be dangerous, so we could just suck off a bunch of these excess electrons created by the gropal and ice and everything rubbing against each other. We could maybe protect some area from getting struck. We could just get this lightning into a lightning rod and dump it into the earth or whatever.
Divert it off someplace safe as opposed to in the middle of your outdoor concert or whatever.
Yeah, exactly. I mean, I guess it would be really hard to use it as a weapon because it has to shoot right at you.
You have to have some guy standing there with a laser. So.
Yeah.
There are lightning guns. There was a Pop Press article on it a few months ago. In essence, they take two lasers that can ionize gas, and then they take a Van de Graaff generator, and then they just shoot the two ionizing lasers at something connected to this charge difference, and the charges move it down one channel of ionized laser through the person they want to fry, and then back up the other one. So, yeah, no, lightning guns exist. I think the Navy was building them, if I remember correctly. So, want to talk about thunder?
Sure.
Banana-nananana, thunder. Banana-nananana. Anyway. Okay, so thunder. When you were a kid, did you ever hear that thunder was two clouds rubbing together?
No.
Okay, just me. That's okay.
I heard that too, don't worry.
So, I'd heard multiple things, but consensus said that it was two clouds rubbing together, whatever that means. But it turns out that thunder is literally the sound that lightning makes. The light in lightning comes from the electrons bumping into gas as they move down this tube. And that causes the gas to heat up really, really fast. 30,000 degrees Celsius.
Lightning is actually 5 times as hot as the sun's surface, so it gets very hot.
Wow.
So this tube gets 5 times the temperature of the surface of the sun all at once, like in milliseconds. And it doesn't have enough time to expand out. And so what happens is it explodes out. It makes a shock wave. The shock wave lasts about a meter until it turns into sound. But in essence, that whole tube of light exploding is the sound we hear as thunder. Now here's the neat bit. The sound you hear of thunder reflects the shape of the lightning. So, depending on where you're standing and depending on the shape of the lightning, you're going to hear thunder sounding in different ways.
So that's why a big, elaborate forking flash of lightning seems to come with a louder and longer crack of thunder.
Right.
I never knew that.
Yeah. And what more? Okay, so you know how lightning, the path that lightning takes, is made up of these 50-meter tubes connected end to end?
Yeah.
The orientation of that tube will determine how the thunder sounds to you. So if that tube is oriented perpendicularly to you, all of the sound coming from that tube will come at you and hit you at the same time. And so you hear like a snap. If the tube is pointed straight away from you, then it's going to take a little bit of time for the sound from the back of the tube to reach you. So the sound at the front of the tube will reach you before the sound at the back of the tube will. So then you'll hear a more elongated boom. And so what happens is, because the lightning jags on its way up, because there's all these different orientations, you're going to hear sound that comes from the nearest part of the lightning to you first, and then the shape of the lightning is going to determine the sound of the thunder as it reaches your ears. So it will go, depending on exactly what the shape is. And each different orientation of each different jag will determine what the next sound that you hear sounds like.
So thunder is kind of a sound sculpture.
Yeah, it's a sound sculpture.
That's very cool.
Incidentally, there's that old trick you learned as a kid where sound travels much slower than light. You can see lightning, count the number of seconds, divide by 3. That tells you how many kilometers away the lightning was, right?
Yeah, or divide by 5 for miles, being a backwards American was the version I learned.
Right. Lightning trivia. Did you know that at any time on Earth, there's about 100 lightning strikes per second?
I did not know that.
Okay, Amanda, tell us about lightning on other planets.
So one of the fascinating things about lightning, I think, is when you look at it on a global scale, so the whole planetary scale. So there are about 2,000 thunderstorms that are occurring on Earth at any given time, which is producing these 100 lightning bolts at any given time. And since we're encompassed in this ionosphere, we have this big cavity around us that actually allows electricity to flow through it, that sort of traps in all the energy from the lightning. So all of these bolts are causing this resonance to happen. We have an electromagnetic heartbeat around the Earth. And it works at a really low frequency, so it's something like 8 hertz. But because of that, we can understand the different composition of the chemicals in our atmosphere. And you can use this technique to go to other planets to understand the chemical makeup of their atmospheres. But in order for that to work, you need lightning on other planets. So we have searched for lightning on quite a few other planets. The candidates would be Venus and Mars and Saturn, Jupiter, and Saturn's largest moon, Titan. We've seen lots of evidence, actual images of lightning on Jupiter, which is pretty exciting. You can imagine that these are like super lightning bolts because while you have the top of the storm at about the same pressure as the Earth, the storm goes a lot deeper into the atmosphere of the planet. So you get a lot more length of the bolts that go through. So on Jupiter, you see lightning bolts all over the planet. There's not a specialized location in the same way that you see it in most places on Earth. But on Saturn, interestingly, you only see it in this one region in the southern part of the planet that they call Storm Alley. So it's this massive storm that's been raging for a long time. You can actually see it with small telescopes from the Earth. You can see it picking up and getting really strong for months at a time, and then it kind of goes away. We've been able to detect lightning through magnetic pulses and radio waves, and only recently have we actually been able to take photos from Cassini and the other spacecraft that have been traveling around. Take actual photos of the lightning on the planet. And you know how hard it is just to get a photo of a crack of lightning on Earth. So imagine these spacecraft up there trying to capture the lightning there. So you would think that, in principle, the lightning there is going to work based on the same physics as lightning here. So the presence of lightning there would infer that there's going to be some sort of water in liquid and ice form. So that's pretty exciting. But it's possible that the same physics, the same separation of charge could occur from rain that's not made of water. So what if you've got methane or ammonia or something like that, as in on the moon Titan? You've got methane rain instead of regular water rain, but the physics should ideally be the same in a nice, well-behaved universe. So lots and lots of different teams have been looking at Titan for many years now, trying to find evidence of lightning through radio and magnetic pulsations and just visually. And even though we expect it to be there, we've not seen any evidence, quite frustratingly, no evidence whatsoever of lightning on Titan. So this is a big mystery, actually. We have no idea why there isn't lightning when it seems to be that it should have lightning. Let's see. So Venus also has a very thick atmosphere, and we didn't see lightning for a long time, but recently there has been evidence based on the radio frequency, so radio pulses. We've seen evidence for lightning there. No actual photographs, though, no images. And the other one that I find fascinating is Mars. So Mars doesn't have clouds in its atmosphere in the way the Earth does, but it has these huge dust storms that go around, which is good for the rovers that are living up there. But these dust storms, the particles kind of rubbing against each other, they cause enough of this charge separation that it's believed that they can create lightning inside of them, as opposed to the clouds where we get it on Earth. So that has been kind of loosely detected. It's not a solid, yes, we found lightning there, but that's one possibility. So the fact that some of these planets have lightning, in addition to just being pretty great and producing great pictures, we try to use this resonance that I talked about before to get an idea of the composition of the atmosphere of the planets. So we look for how much water there might be, how much ammonium, how much methane. And ultimately, this can help us understand how our entire solar system formed, or what the big cloud was that our solar system formed from. Because the field of methane and ammonia that's in Jupiter's atmosphere is a bit different than what we've seen in Uranus and in Neptune. And there's no good explanation for why that should be different. So if we can get some understanding of the actual amount of those in the planets at different distances from the sun, then we can really start to understand and test our theories for how our entire solar system started, all thanks to lightning.
That's insanely cool.
Well, that was fun. So thanks, Zach. Thanks, Amanda. You pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. Okay, Zach, you get a banana.
Oh.
Yeah, it's the lightning of the fruit. And Amanda, you get the thunder of the fruit, the mighty coconut.
Nom.
Awesome. Okay, I'd like to thank my guest, Elizabeth Bear. Elizabeth Bear, thank you for coming on so much.
Thank you. I've had the time of my life with you guys.
Oh, we've had so much fun with you. We hope we answered any questions that you have.
I feel thoroughly edified.
Yay! Okay, fans. Let's suppose you want to interact with the titanium physicists a little bit more. If you'd like to keep track of us, why not follow us on Twitter at Titanium Physics or join our Facebook group? If you'd like to hang out with us and socialize, why not join our online forum? Or if you'd like to send me an email directly or ask a question or propose a topic, email me at barn@titaniumphysics.com. That's BARN at titaniumphysics.com. So let's suppose you want to listen to us more conveniently. If you've got an iPod or an iPad, try subscribing to our show on the iTunes Store. While you're there, write us a review. Your reviews determine our ranking on the iTunes Store, which in turn determines how many new listeners will discover our show. If you have a Zune or a BlackBerry, you can subscribe to our show on those doodads as well. Or you can download the Stitcher Radio app, which lets you subscribe and listen to all your favorite podcasts. You can download the Stitcher app for free onto your iPhone, Android phone, Kindle Fire, or other devices. Stitcher's convenient because it lets you subscribe to your favorite podcasts and listen to them easily. Okay, for all this and more information, visit our website at www.titaniumphysics. The Titanium Physics Podcast is a member of Bracula Media. If you've enjoyed our show, you might enjoy Science Sort of, or the Weekly Weinersmith.
The Weekly Weinersmith.
All right. Check them out. Check them out. So the intro is by Ted Leo and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
As a physicist, I have absolutely no training in the physics of the atmosphere. For some reason, studying clouds is completely off topic for any class I've ever taken. So it was really interesting to me to look up into the sky and try to guess the physics involved in it. So one obvious thing with the atmosphere is that it's warm down on the surface and it's cold way up high, right?
Mm-hmm.
So you might ask yourself, hot air balloons rise. Why doesn't this warm air just bubble up into the higher atmosphere? Why doesn't it warm up top instead of down at the bottom? The interesting answer is that it kind of has to do with the thermodynamics of the gas. As you go up higher in the atmosphere, the pressure decreases, and so if you took a bubble of gas and you brought it up into the upper atmosphere, the gas would expand because of its higher pressure, and as it expanded it would cool, and it would end up colder, in fact, if you took a bubble of gas and took it way up high into the atmosphere. The story changes a little bit if you have really wet gas, full of vapor. So if it's a really, really humid day, if you take a block of really humid gas and you let it rise up into the atmosphere, what happens is the latent heat and the heat capacity of the vapor in this block of gas as it rises up will keep it warm. In essence, it's kind of like if you take a water bottle out of the fridge, how it stays cold for a long time, even in air. As you take this block of damp gas up into the atmosphere, it stays warmer than it should for much longer as it goes up. Essentially, to form a cumulonimbus cloud, you have a bunch of really hot gas near the surface of the Earth. It's not really hot. It's, hot summer afternoon temperature, but it's really damp. So in the end, it can rise a lot longer. And cumulonimbus clouds, as a result, end up much taller than any other cloud formation. They're those thunderhead clouds. In essence, the system is unstable at the very start, like drawing back a slingshot. This big column of air rises up high into the atmosphere, and you get a cumulonimbus cloud. If a cumulonimbus cloud was above you, it would be about 2 kilometers above you. So that's about 1.5 miles. But then it goes about 16 kilometers up to the top. So it's really, really, really tall. It's about 14 kilometers tall, depending on where you are.
Now, I've noticed that they tend to shear off at the top. Is that generally because of air mass or wind moving in a different direction from the cloud?
Yeah.
Is that what sets the limit on their height?
Actually, so if you took a marble and you put it in a slingshot and you shot it straight up, it would go up, reach a certain height, and then fall back down, essentially. Mm-hmm. And essentially something very similar is happening to this water vapor. It starts out really, really hot. It starts to rise like a hot air balloon. And as it rises, it gets colder, it starts to expand, and as it cools, it's going to keep climbing until the temperature of that ball of gas is as cool as the ambient temperature at that altitude. So as it cools, it gets colder and colder and colder, and what happens is the water vapor in it starts to condense.
So the height of the top of the thundercloud, it's also very dependent on the pressure. So you get lower and lower pressure as you go higher and higher up. And an interesting comparison between Earth's thunderstorms and other planets is that the top of them is all defined by this one standard pressure. It's 0.1 bar, if that unit means anything. But it's the same pressure that defines the top of these storms. And then the bottom is completely dependent on whatever temperature your planet happens to be.
So if you're talking about a megastorm on Saturn or something, it still tops out at 0.1 bar.
Yeah.
That's really cool.
I thought so too.
Okay, so cumulonimbus clouds are fairly violent on the inside. Essentially, you have this big mass of hot, dense air. It rises up, and then the vapor in it condenses. And because it condenses in fairly cold regions, and because it moves upwards so quickly, it ends up supercooling the water vapor in it. The way supercooling water works is that if you take water, like a cup of water at sea level, it starts to freeze at 0 Celsius, right? So at 0 Celsius, it turns into a block of ice. But it turns out you can keep it from turning into a block of ice if you can keep the crystal from forming. So if you stir it, you can keep these crystals from forming, and essentially the water will be cold enough to freeze, but it just won't have a chance to crystallize. And the crystallization happens really suddenly as soon as it gets a chance. And so water in that state is called supercooled, and essentially that's what happens to these droplets of water up way high in the atmosphere at the top of these cumulonimbus clouds. And so when some snow particles or some ice particles come in, the water and makes a little ball of ice around each snowflake. And this is called gropal. You ever heard of gropal before?
I have not.
It's called soft hail, but in essence, what happens is you get this gropal ice up high in the atmosphere that's then too heavy. The air supporting it is no longer buoyant, and then it falls down. All of this gropal, all of this ice, all of this snow falls down in a rush, straight down. That's called the downdraft, and it brings a column of air down with it. You think about when you've been outside in a thunderstorm, the temperature drops really suddenly. It goes from nice hot day to pretty cold all of a sudden. That's that massive cold air from the top of the cloud rushing down and hitting you. And then immediately after it starts to pour rain. Instead of a nice, happy half-hour rain shower, it all comes down in a rush. And so you end up with a fairly short, they only last about 10 minutes, but a really, really intense rain, right?
Right.
Right. Okay. So, in essence, that's how cumulonimbus clouds work. Okay. So, right. Hold on. I've got, so
I gave a bit of a layman's
the moral
term,
of the story is that
kind of what I would say to my niece or nephew.
Yeah. I've got a great explanation.
Can we talk
for all
about
these things.
ionizing air? I feel like that's the concept that elucidates everything, at least to me.
Okay, yep.
Yeah. Let's start.
Do you want me? I think Ben could do a better job.
Okay.
I should say that this podcast is incredibly fortuitous for me because I'm actually working on a story right now for the online serial I work on, Shadow Unit, which involves controlling where lightning strikes.
Oh, awesome.
So,
We actually there's a scientific experiment where they basically did that. We can get into once we do a little more.
Right.
So you guys are doing my research for me. This is fabulous.
No, this is awesome. Okay,
Our pleasure.
so
I think it's really fascinating that it happens. Did you say it was 50 microseconds? Is that?
yeah.
Oh, it's always exactly the same interval.
Well,
I find that kind of fascinating.
it's I probably 50 microseconds is a Wikipedia number.
Oh,
I mean, it's it probably takes around that. There's probably some variation. I would bet my hat, but
Yeah, it's hard to imagine a situation where there wouldn't be some variation.
yeah. But in essence, it's probably due to the amount of time it takes to ionize the gas, and for the electrons to move from the big dense mass of electrons down into the new extended tube.
so it's not Cloud Spirits playing some advanced version of Ticket to Ride.
No.
Okay, that was an obscure joke. I'm sorry.
I liked it.
Okay.
Can I talk about this cool thing I found at Worldcon?
Please do.
So I'm sitting at a signing table in the dealer's room at Worldcon, and as I'm sitting there signing books, I'm realizing that the dealer across from me has these blocks of acrylic that have fractal branching patterns in them. And after I've been staring at them for about 15 minutes, I realize that they're Lichtenberg figures, which are the patterns that lightning makes when it strikes something. A human being, a golf course, a tree. They look like roots. And so after I was done signing, I went over to these guys, and I had a fascinating conversation with this guy, Todd Johnson. It's capturedlightning.com is their website. He explained to me what they do in a conversation that began, first you rent a particle accelerator, which I think is my new favorite sentence in the English language. So they take these blocks of acrylic, they run them through the particle accelerator. They basically put an immense static charge on them. And then when they get them out the other side, they take a metal rod of some sort and discharge them from a point. And you get, I guess, vaporization trails through the acrylic.
Sweet.
How cool is that?
That's so cool.
And they have all kinds of, they can make them three-dimensional by shielding different parts of the acrylic. And apparently what they will do is shield part of it, charge it, turn it over. I asked him how they turned it over. He said very carefully. Shield another part, charge it again, and then discharge it, and they get these swirly patterns.
Amazing.
It's really neat stuff. And I may have embarrassed myself squealing about the coolness of it.
What are they pronounced again? Lichtenberg? Here.
Lichtenberg, was it?
Yeah,
Lichtenberg.
Lichtenberg figures, or Lichtenberg. I think it's Lichtenberg. Lichtenberg.
Yeah, we looked them up, and sure enough, they're essentially it's the wounds that is left behind on a material as the stream of electrons tries to escape as best as possible. And they kind of, they form kind of arteries as they follow the paths the previous electrons have traveled down, and then they try to optimize area, so they branch out essentially like a root structure. And so when people get hit by lightning, this is kind of what it looks like on their skin afterwards. There's some horrific photographs on Wikipedia.
Yeah, the effects of lightning on human beings is actually something I've been researching again for this story.
Horrible.
And what they call them lightning flowers when they're on a human being.
That's a lovely euphemism, isn't it?
Yes, it's a lovely euphemism for horrible burn scars. Lightning also has profound neurological effects on people, which is really fascinating. There's this guy who, I think he was a mathematician or a physicist who was struck by lightning and suddenly decided he wanted to be a concert pianist, so he became one.
Huh.
And had never had any urges in that direction before, but just became obsessed with this. I guess music and mathematics are related fields. If you go to YouTube and look up Lightning Sonata, you can hear one of his compositions.
Oh, fun.
Yeah, I've read. Oliver Sacks wrote about him a bit, I think, and that's interesting too because when electroshock therapy works, I think a similar principle. You basically give the brain a really hard dose of electricity, and sometimes you get really interesting results. For example, it's still used for depression curing.
So it turns out that how the stepped ladder works and why the lightning flashes the way it does.
Step lead. I think you said step ladder.
Oh! Okay, for that, oh, that's alright. Okay. That's right. In fact, fluorescent lights. So in fluorescent lights, essentially, it's something similar is happening. You've got these two leads inside this tube, and the tube is full of gas, and these leads are above the breakdown voltage of the gas. And so you get one electron, and it cascades down the tube, knocking off other electrons and shining light. And so, you know what a ballast is in like in a fluorescent light, right? It's this big block.
I know they exist.
Yeah, who knows what they do, right?
I could not claim to know what their engineering purpose is.
Yeah, well, I mean, you don't want to throw them in landfills. That's all I really knew about them. But in essence, what those are there for is they're there to keep the cascading ionizing electrons from growing out of control. Because as these electrons cascade down, they knock down other electrons, and the more free electrons there are in this gas, the more conductive it is. The resistance of the thing goes down. You've heard of a short circuit before, right? Mm-hmm. So you take two leads and put them together. There needs to be some kind of resistance to push through it, or all of the electrons move from one to the other, and a whole bunch of heat's generated, your system blows up. In essence, inside one of these fluorescent tubes, if they let this electron cascading get out of control, the electric tube can short circuit. The resistivity can go to zero if you let it go on too long. So that's why they flicker, and that's what the ballast is for. It's, in essence, in fluorescent lights, they turn it on, the gas gets hit by electrons, the gas becomes more and more conductive, and then they shut it off before it gets too conductive. And they let it cool for half a second, and then they restart it. So it goes on and on and on and on and on. So in essence, fluorescent lights are just lightning in a tube.
Neat.
Let's talk briefly about lightning rods. Do you know how lightning rods work now? Can you guess?
Well, I'm guessing that, in general, one tries to make the lightning rod the highest point in the surrounding area.
Right.
And I would assume that the step leader hits that first and channels into it.
Right. Actually, you want the positive streamer to kind of come off it. What'll happen is, it's a rod of metal, so it's a good conductor first off. When you have this great big concentrated electric field coming off your negative charges, coming towards the Earth nearby, what'll happen is they'll push all of the electrons out of it. And so you'll have a really strong positive charge on this metal rod. And then, just like how the step leader, how it can cause a breakdown of the gas only at the very tip of it.
Right.
You can take a similar advantage of that on a lightning rod. Essentially, it's a rod-shaped, because what'll happen is, off the very tip of that is where you'll see the air breaking down. So you'll end up with tubes of ionized gas, essentially, coming off and connecting to the very tip of this metal rod. And that way, when the lightning comes through, that positive streamer will be moving up, connect to it, and then maybe it won't have to hit your house or something like that. So incidentally, that's why things like golfers get hit.
And why you're not supposed to stand under the only tree in the field. Yeah,
it's because these pointy things have really strong electric fields off the very tip of them, and so they're more likely to get struck by lightning.
Aha! Which would also be why things like church steeples and tall pine trees tend to get hit.
That's right. Incidentally, it's just like you're starting your own stepped leader. I was telling you before how we don't know exactly how these step leaders get started. We don't know where the first tube of charged gas comes from. It's in essence, what you're doing is you're starting one yourself that's coming out of the ground. And that one's going to go up into the sky and channel the lightning down through metal instead of through your precious belongings. But incidentally, what happens is lightning sometimes hits trees, as you mentioned. You can actually identify trees that have been hit by lightning. It happens a lot. What happens is sometimes the lightning will hit a tree And all of the electrons will pass through the sap of the tree. When electrons move through things, they bounce off them. There's essentially a lot of friction, what it comes down to. It heats things up. It heats them up so fast that the sap in the tree can turn into gas and explode. So what you see in the tree is part of the bark has exploded.
I've seen this in my own backyard. It's reasonably impressive.
You see these, essentially these little scar marks, these little holes in the bark, and that's where the bark has exploded because it's been hit by lightning.